Hello grade 11s, sorry I'm still not going to be back at school tomorrow, so I've made a video for day 3 which is properties of matrices. We're going to look at some properties of matrices, we're going to talk about finding the inverse of a matrix, and we're going to start to look at how we can use both those things to solve some matrix equations. So there's a little bit to do today. Okay, so let's start with some properties of matrices. Really there's just some facts about matrices. So if we have a matrix A squared is defined as A times A, much like just with a regular number. We know 4 squared means 4 times 4. Same is true for A cubed, A times A times A. We looked yesterday at the fact that matrices are not commutative. So matrix A times B is not the same as B times A. The distributive property does hold for matrices though. So we can, if we have matrix A multiplied by B plus C, we can distribute that to AB plus AC. So in that respect, it acts a little bit more like we're used to. And of course you can verify that by checking this calculation here. You can do it once by distributing and then adding the results, and you can do it by adding first and then distributing. Then multiplying. Okay, so I'll leave you to do that. I will fill in the notes so you can check those if you like. We're going to move on to inverses. So with square matrices, we can find inverses, and we write it as a to the power of -1. And it's a bit like when we talk about function notation. It's not really that idea of a power of -1, it's representing the inverse of a. It is more similar to the idea of a reciprocal with numbers in some ways. Like we know that 3 to the power of -1 is actually 1/3. And if we do 3 multiplied by 3 to the power of -1, it's 3 times 1/3, which is 1. This works the same with matrices. So A times its inverse is the identity matrix, and the inverse of a matrix times the matrix itself is also the inverse. You need to be able to find the inverse of a 2x2 matrix by hand. You will not be required to find any larger matrices inverses by hand. You can always use your calculator for that. So there's an investigation here. It's not the simplest investigation. You decide how confident you're feeling with it. The algebra gets really quite messy with it though. So it could be one that you decide, actually, I'm more interested in the result. The investigation is not important for our course, but it can be. I know some people like understanding where kind of the background of it. So if you'd like to try the investigation, pause the video, have a go at it. But yeah, fair warning, the algebra gets quite messy. Once again, I'll put results on OneNote for that. Okay, so maybe you had a go at the investigation, maybe you didn't, but it leads to this result, which is how you actually find the inverse of a matrix. So it's down here. This is all in the formula guide. If we've got this matrix A, B, C, D are the elements of it. If we want to find the inverse, you'll see it's pretty complicated what's going on. We're going to kind of piece it all together though. So I'm going to start by taking the first bit, this fraction. AD minus BC is at the bottom of this fraction, so that means taking the elements A times D minus B times C. Okay, so easy to calculate. That is actually, this AD minus BC part is actually called the determinant of A, and that's an important term that will come up again and again. Sometimes it's written det A, or sometimes it's written as the absolute value of A. But here we've got 1 over that determinant at the front of our matrix. Okay, let's look at the rest of it. You can see that the A and D have switched positions. So when we look at matrix A, we've got A in the top left, D in the bottom right. They have switched positions in our inverse. And you'll notice that the elements B and C have not moved, but we changed the sign. So there's a lot that goes on, but as I said, it's all in the formula guide. We are in topic 1 here, and we're in the HL section. And you can see we're down kind of 1.14 here. So we've got the determinant of a matrix. This is that AD minus BC. And then we've got how to find the inverse of a matrix. So you're not expected to learn that formula. You're just expected to be able to apply it. So to find the inverse of this, we're going to start, well, let's call this matrix A. We're going to find the inverse of it. So we say it's 1 over the determinant, that is AD minus BC. Okay, I'll leave the formula up the top there. And then you can see we start our matrix. We're going to switch A and D around. So the 2 and the negative 3 are going to switch positions. And then B and C, we change the sign. So 1 becomes negative 1, 2 becomes negative 2. Okay, that's that done. Let's tidy it up a little bit. What have we got on the bottom here? Negative 6 minus 2. So let's call that negative 8. There we go. And there's lots you could do with that. You could decide you want to multiply that 8th in. You may decide you want to keep it out. You might decide because there's 3 negatives inside the matrix and a negative outside, maybe it's better if you multiply the negative in, or the negative 1 in. Yeah, lots of ways you could leave your result. And basically, if you get down to this stage, we are happy. Okay, it says check the inverse, multiply the matrix is equal to the identity matrix. So we're just going to check, is A times the inverse of A equal to the identity matrix? So we'd need to do 2, 1, 2, negative 3 times an 8th times 3, 1, 2, negative 2. Okay, I'm going to move the 8th out to the front, and then I'm going to multiply my matrices. So row by column, 2 times 3 plus 1 times 2. Row by column, 2 times 1 plus 1 times negative 2, and just keep on going through. So I'm on second row, first column, minus 3 times 2, and then 2 times 1 minus 3 times negative 2. Okay, let's tidy this all up. We've got an 8th out the front. We've got 6 plus 2 is 8. 2 minus 2 is 0. 6 minus 6 is 0. And then 2 plus 6 is 8. And of course, an 8th times this is 1001, which is I. And that is the result we're after, that A times its inverse is the identity matrix. We can find these using our calculator as well. So if I take, let's have a quick look at this. 2, 1, 2, negative 3 is my matrix. 2, 1, 2, negative 3 is my matrix. And I want to raise this to the power of negative 1 so it finds us the inverse. Okay, you can see they have pulled the 8th in. I've pressed the fraction button and I can see those 8ths. So yeah, that's how your calculator is writing it. And it means that you can use that for larger square matrices. So we can look at example 4. You can use this, same idea. Here we are, we're going to put in 4, negative 3, negative 2. Then 2, 2, 3. And then 6, 1, negative 1. And let's raise it to the power of negative 1. Okay, that's not very nice. Let's see if it looks better as a fraction. It does. So yeah, I'm just pressing this fraction button up the top, and it's switching between decimals, fractions, and I don't know what it did when I did that. Yeah, I'm not sure what the difference between the second and third is, but there we go. So P negative 1 equals, okay, we've got 12ths all across the top. Then negative a third. Okay, I'm imagining you're probably going to want to skip this instead of watching me copy these down. 6th, 11/30, I can't remember the last one, -7/30. Okay, so that's our inverse matrix. And once again, we can verify that multiplying that by its, let's multiply this times, what did we have before? I want to get rid of the power. So that is the inverse times p is, well, it's not perfect, is it? But it's very close. 1, 0, 0. Then we've got a tiny number which we should interpret as 0. Then 1, then another very small number which we interpret as 0. And then along the bottom we've got 2 small values which we interpret as zeros. So yeah, we've got 12 zeros out the front of those. So a little bit of interpretation of our calculator there. But yeah, it is multiplying to give us the inverse. Okay, so that's how to find the inverse. As I said, you will be expected to find 2 by 2 matrices either with technology or without, and there'll be times where you do need to do it without technology. Anything bigger than that, you are not expected to. It gets really quite a lot more complicated, even just moving up to a 3 by 3 matrix. There are some matrices that don't have an inverse, and the reason they don't have an inverse is the determinant is equal to 0. So if we go back to this formula, you'll see why that's an issue. So this bit down here was the determinant. If that equals 0, then obviously we've got 1 divided by 0 out the front of our fraction, out the front of the matrix in that fraction, and we cannot, of course, do 1 divided by 0. So it means that you will end up getting an error when you try and find the inverse. So that is a proviso. It's an important result. I'm highlighting this, which means it is a result to memorize. In particular, that word singular means the matrix is singular. Or if you're told a matrix is singular, it means it has no inverse, and it also tells you that the determinant is equal to 0. One of those facts that you need to be able to use in both directions. Okay, so the main reason at the moment while we are kind of building up to these inverse matrices is so that we can solve some matrix equations. Now, there will be some similarities with solving matrix equations when you compare it to kind of just solving regular linear equations, but there will also be some differences. And the main differences come from that fact that matrix algebra is not commutative, so the order is very important. So we've got an equation ax equals b, where a, b and x are all square matrices. This can be solved to find x. So just like if this were just, if they weren't matrices, if they were just kind of a mixture of variables or unknowns, we would of course just divide by a on both sides. And then that would help us isolate x. We are not looking at dividing by matrices. We're going to use their inverses instead. So instead of dividing by matrix A, I'm going to apply the inverse matrix to it. And of course, that means I've got to do the same to the other side. And the reason we do that is because those two together make the identity matrix. You'll notice I applied this to the front of AX, so I apply it to the front of B because the order is important. I have the choice of multiplying to the end of the matrix or the beginning, and so I have to make sure I do the same to both sides. So these two make the identity matrix. So what we end up with is x equals the inverse of A times B, because the identity matrix is effectively like multiplying by 1. There we are. So we would just say this. If you were actually doing this, answering questions like this, you would probably not bother writing out this step. But as it's the first time we're doing it, I'm of course writing it out. So if the equation was the other way around, let's make a bit more space here. So we just switch the order of x and a. I don't want to apply the inverse of a to the front of this, I want to apply it to the end, and so I'd do the same here. So that's our identity matrix. We've got x equals b, a inverse. So slightly different result. If this were non-matrix algebra, we would end up with the same thing, x equals b over a. So it's just highlighting the fact that the order is really important. Okay, there's some examples to have a look at on this page. I think that I'm going to put workings up for question 1. I think I might go through questions 2 and 3 though. Okay, so I would pause the video, have a go at question 1, kind of leads on from what we were doing before. Okay, you're back, so hopefully you're taking a look at question 2. We want to find x, y, so that is here. Okay, so we need to try and approach it with the algebra skills we already have. So if this were just an equation, and I've got something times my unknown plus another number equals another constant, I would start by getting rid of this. And that's the same with matrix algebra. I'm going to subtract this 2 by 1 matrix, 2, 3. So let's keep this where it is. We've got x, y, and I'm going to subtract 2, 3. So 3 minus the 2 is 1. 1 minus 3 is negative 2. There we go. Okay, my next step. I want to get rid of this matrix out the front, so I know I need to apply the inverse matrix to get rid of it. So I'm applying that to the front of this, so I apply it to the front on the other side of my equation. All right, so this front section is just I. It's like having a 1 out the front. We can ignore it now. And you could do this algebraically. You could find the inverse, then you can multiply it by 1, negative 2, or you can get your calculator to do all that for you. So let's have a go at doing all that in one go. So negative 1, negative 3, and then 1, 4. And that was the inverse of it multiplied by 1, negative 2. Okay, I'm going to go for this one here, 1, negative 2. There we go, so that's our answer, 2, negative 1. X is 2, y is negative 1. Okay, the final example today. If a squared equals a plus 2i, find an expression for the inverse of a in terms of a. All right, not so obvious about what we need to do here. We need to find the inverse of a, so I'm going to have to introduce that somehow. And one approach would be to just, in fact, that's probably the approach that we should go for, is just to multiply both sides by the inverse of a. We know we need it in there somewhere, so if we start with that, we can get an idea of where we're going to go next. If you have a good idea, if you're fairly confident with your matrix algebra, you could probably see some steps you could start with that would maybe make this a little bit slightly easier. But let's go from here. So if I take the left side first of all, you'll remember that a squared is just a times a. So I'm just going to write all those together. And you'll also remember that we're allowed to distribute with matrix algebra. So inverse of a times a plus the inverse of a times 2i. Okay. Right, let's go through each of these terms and figure out what's going on. This is the identity matrix. So I'm left with just a. This is the identity matrix. I'm not going to get rid of it because it's not being multiplied with anything, so I need to keep it. It's like having a 1 in your equation. You don't just get rid of 1 on its own. We're going to keep it there. Okay, what's going on with the rest of this? Let's switch the order around. 2. So I'm switching the order of the scalar multiplier. I'm moving that out the front because that doesn't matter so much. I've kept the order of the matrices the same, although looking at this, the end matrix is the identity matrix. So it's like multiplying by 1. I think I can actually just get rid of that. Okay, so I've got 2a to the negative 1 and 2, the inverse of a. And if you remember, we're trying to find an expression for the inverse of a. So I've got that in the equation now. I just need to get rid of the other things on this right-hand side of the equation. So I'll start by subtracting my identity matrix. Okay, I can't get rid of I. Remember, it's like the number 1. If we've got x minus 1, you can't get rid of 1. If you've got x times 1, you can. So a minus 1, I'm going to keep that there. And then I just want to get rid of the 2. So I could do a half to both sides. Okay, so now I have an expression for my identity matrix. I'm going to write it out the right way around now. So that is the alone on the left-hand side. It's in terms of A. I do also have this matrix I, but that is the identity matrix. I don't have any A squares. I don't have any other matrices. I'm pretty happy with that. I think if you were able to think a few steps ahead, you probably could have done some rearranging before you introduced that inverse of A. Maybe you'd realise that the inverse of A, to make it the subject, it's going to come from when you multiply the identity matrix by the inverse of A. So maybe you'd start by rearranging first of all. But I don't think it's a big deal. We've managed to get there. We have, we've used this idea of the distributive property. We've used the idea of getting inverses and identity matrices. So hopefully that is all clear. Okay, there's quite a lot to practice here. There's a lot of new skills, but yeah, we're going to keep using those next lesson.